theta, you know that from point B over here, this is your FAB. Okay, your FAB from point B is pushing towards the what? It's pushing towards the element, towards the member AB. And this is over here, this is your member AB. I'm going to draw this. This is your member AB, right? So this is your point A, and this is your point B, right? And a lot of you say member AB is in tension. You are absolutely right. Right? Yeah, absolutely. So member AB, a lot of you say that this is in tension. So if you look at FAB now, it's pushing towards the what? It's pushing towards AB. But based on Newton's third law, action is equal to reaction, same in magnitude, different in direction. That is why it's in tension. Okay, so this red arrow over here is based on Newton's third law. Okay, so Newton's third law is action will be equal to reaction, same in magnitude, different in direction. I do apologize, okay? It's really messy now. So that is where member AB now is in what? Tension, okay? Now let's look at member BC. So we realize over here, because of ABX is pushing towards the left-hand side, and we know that point B has to be stationary, we need a reaction force over here, right? We need a reaction force over here. So this reaction force will be BCX, and this is also equal to our FBC, right? Because BC can only hold a horizontal load based on truss analysis. So when that's the case, action is equal to reaction. So action is equal to reaction. So this is your member BC. Oh, sorry. So this is your member BC. Again, you apply Newton's third law. Action is equal to reaction. Same in magnitude, different in direction. So that's where member BC is in what? Compression. Okay. And then if you were to find your FBC, so we know that summation about forces in the x direction is equal to 0. So from here we have our ABX, so we have our minus ABX plus by BCX is equal to 0. So we have BCX is equal to ABX, and this is equal to FAB. Okay. So two different ways of analyzing the structure. Outcome is the same. So one is based on deformation, right? So some of you have very good visualization because you play a lot of Lego, for example. Okay, you can use this technique. Those of you that don't have that visualization skill or don't have the confidence yet, you need rules. Okay, so this is the rules that how you could identify whether the structure is in tension or in compression. But more important of all, I've convinced you that in truss analysis, right, you are doing what? You're focusing on the what? Axial loading only. Okay, you are not considering the bending moment and the shear force, which we will do later. Okay, does not mean okay, that's it. Okay, you're good to go. No, we'll assume later. Right. Before I go on, any questions, please, regarding method of joints or regarding any of what I've shown, please. Thank you. Anyone? No? Is the lecture too quick for you guys? Or we are okay?
It's good for me.
Okay. So if I'm going way too quick, also you can also tell me, excuse me, Can you please slow down? By the way, don't call me sir or Dr. Ng, okay? I will hit you online, okay? Call me Eugene for crying out loud, okay? Right. So let's see how we analyze structures now. Okay, so how we analyze structures. So now structures can be analyzed okay, can be designed based on reaction force. Okay, it can be designed based on reaction forces. So what do I mean by that? So based on reaction forces, we know that if this is our member, right? All we need is to find, like what we've done earlier, is to find P. And we have a couple over here. That's P prime. Okay, so once over here, we will say that axial load will be equal to force P divided by area. So we just have to ensure that the axial stress that we've calculated is less than our stress allowable. Okay, is less than our stress allowable. And the stress allowable is the material property, is the mechanical material property. Okay, so that's how you calculate your stress allowable. Okay, so if we look into, if I were to draw a stress strain curve, okay, so we will draw stress strain curve over here. So this is our strain, this is our stress. When we mechanically load our structure, this is a typical trend that we will see, right? So this is a trend we will see. So can anyone tell me, okay, can anyone tell me what is this point over here that I've circled? Anyone?
Yield point.
Yep, so that, well done. So this is our stress U. And over here?
Ultimate tensile strength.
So well done. So this is called ultimate strength. Now, I know that you just mentioned ultimate tensile strength. I'm not saying that you're wrong, but if it's in compression, it can be also known as ultimate compression strength. So it is dependent on how your structure is loaded. Okay, and this point is known as failure. Okay, failure point. And then I'm going to construct a line for over here, right? And this gradient over here, anyone? What is this gradient called?
This is the slope
The
of
modulus of elasticity.
Yep, you're right. So this is known as your Young's modulus. Okay, and we know on the left hand side is the elastic region. Sorry, on the left hand side is the elastic region. Do apologize. And then on the right hand side is the plastic region. And this you will obey Hooke's law that states that stress is equal to Young's modulus multiplied by strain. On the right hand side, it will be based on stress is equal to A plus by B epsilon PL power of N. Okay, so don't worry about the right hand side equation. Focus on the left hand side. Now, why am I elaborating on this? Is somehow, okay, if you look at textbook, stress allowable, okay, stress allowable or we look at factor of safety. Okay, which we call FOS. So factor of safety will be equal to what? Anyone? Can anyone tell me what is factor of safety equal to? No? How do you calculate your factor of safety? Anyone? Okay, so factor of safety, if you look at textbook, will be equal to ultimate strength divide by stress allowable. Okay, that is your factor of safety. Now, anyone has any comment with this, please? What do you think? Do you think this is right? This is a textbook, okay? If you refer to any textbook, that is what you will get. Anyone?
Why isn't it based off the yield? Why is it the ultimate strength?
Right. Well done. Okay. So one of you say, why do you say that? May I ask why you say that? Why do you say that? I mean, what is written? What is written from the textbook is you can look at the textbook. Okay, it's always ultimate strength. So why do you say that?
Because you want elastic deformation, plastic deformation, then whatever you're looking at is permanently deformed.
Yep, yeah, absolutely right. Okay, so what you're telling me now is factor of safety should be in fact equal to the yield strength divided by stress allowable.
Yeah, that seems more practical.
Yeah, I like that. Okay, so you mean to tell me the textbook is wrong?
Well, it's just an opinion.
It is okay. Now listen, this is what a degree is all about. Okay, know when to use what and why. Okay, don't just take what the textbook threw at you and that's it. Okay, I want to train you guys to be analysts. Okay, not someone that just follow the crowd. I'll give you an example. Recently, we had a coronavirus, right? And everyone rushed to buy toilet paper. Can anyone tell me why?
I still don't know.
Yeah. Right?
Hand soap was available though.
Yeah. So why
Needed.
toilet paper? Because someone decided to buy 50 rolls of toilet paper. Everyone went to buy toilet paper. I think I know. Yes. Anyone? Yes. Right. I could hear someone did not mute the mic. Okay. So it's interesting, isn't it? Right? I did not go and buy toilet paper at all. The only reason why they buy toilet paper, so they will roll the toilet paper into small pieces and put into their nose and put into their ears. No reason to buy toilet paper. That's what I want you all to do. I hope to achieve from this course is not just strength of material. I want you all to have dare to be different and analyze things that are different. Okay, that is the purpose. If anything to do, I'm more interested in training you as a character, as an engineer, and this is one of the best courses to do it. Okay, now, so the yield strength is absolutely right. Okay, but sorry, both of them are right. Okay, however, this is important. This formula over here can only be used for brittle material.